electric potential. What do we know about it? And is this electric potential term is okay to use for a charge or for a group of charges also? Let's see. Actually, potential has a very simple definition. Electric potential means work done per unit charge. Work done per unit charge. Now, what is this work done? From where to where and for what? This thing is quite, if not quite obvious, but it is somehow relating to this point that this work done is for this point charge only. What is this point charge? Unit positive test charge. I have already discussed about unit charge, that unit charges are those charges which are very small in magnitude, the unit magnitude, and they do not affect the presence, the electric field or the electric force of any other charge. So these unit charges are taken into system when we have to find out electric force, electric field due to any other thing. Suppose this is an electric field due to our source charge Q. Source charge, this is the electric field, and I have to find out the value of electric potential at this distance R. Then listen to the definition. According to definition of electric potential, it is defined as work done in bringing a unit test charge from infinity to that point. I would repeat, electric potential due to a charge at distance, at any distance, is defined as work done in bringing a unit positive test charge from infinity to that point. Now, if I have to derive an equation for the electric potential, the value would be very easy because we know the value of work done. Work done is what? Force into distance and divided by unit charge, and I would have got my answer. There is a problem. Force is something which is not present from here to here. How? See, when you have to move a charge in the absence of electric field, and we are talking about this chapter electrostat, what do we say about force? Force is Q naught into E, and if there is no electric field, then the force would be equal to 0. So how would we use it while deriving the equation for work done? This is how we'll do. Consider the point. Right now I'll draw a still bigger diagram because you will be needing it. Let us consider that electric field due to this charge is up to this point, okay? And this is the point which is at a distance r from our charge, at which we have to find the electric potential due to this charge. Our point charge is at infinite distance from the source charge right now. So when I am bringing my test charge from infinity to that point, I'll be calculating the value of total work done, and that will give me the expression. While moving this point charge Q naught from this infinite distance to electric field, there will be apparently no work done because this charge has been moving in the absence of any electric field, hence no force has to be applied on it. Even a small drag can bring this charge to this point. Or you can say there is no appreciable force from this point to this force, because we already know that without any force a body cannot move. So the force is so small that it is not taken into account. It's not considered. So it's unappreciable force. Now at this point, when our charge has reached the electric field, this was Q naught here, when our unit charge is at this point, it is just entering the electric field of our source charge. What will happen? This Q naught will get repelled by that charge, both are positive right now. So this will experience a force which is equal to Q naught E. I am writing the arrows because I am mentioning the vector formation of force and electric field. So if I want this charge to further move in this direction up to this point, I will have to apply a force which will be equal to minus Q naught E, right? Equal and opposite to this force. That's why I am mentioning the sign of force, opposite. Okay, now we have a value of force. So it will still be very easy for finding the value of work done if this force would have been constant, but right now force is also not constant because of the formula. What is F? K Q1 Q2 upon R square. Force is inversely proportional to distance square. That means force will be changing at every point. Due to the changing value of force, I cannot apply the direct formula of force into distance. So we will use the value of integral format or the differential format. How? I would say, or consider the force is right now at a distance, at any distance x from this charge. Okay, this distance is x right now up to here, and let us say a small amount of work is done in moving this charge by a small distance dx, right? This will be using at the end. Let dw be the small amount of work done in moving this charge by a small distance dx from this point to this point. So dw would be equal to F dx. What is F? The force which we applied was minus Q naught E. Why I am taking negative sign here? Because work is a scalar quantity. We have to consider sign wherever it is applicable. Therefore, total work done, this is W. Total work done in bringing the charge from infinite distance to R distance would be integration dw infinity to R. Now our system is clear. We will just write the value of from infinity to R. What is dw? Minus F dx. What is minus F? Infinity to R. What is minus F? Minus 1 upon 4 pi epsilon naught Q naught upon R square or X square. Right now I would be using X because we have considered it to be at X distance, right? And that is why we are integrating it for a smaller value dx. I am visible in the field, so from this take all the constants out. What are you left with? Work done is equal to minus 1 upon 4 pi epsilon naught Q naught integration dx upon x square. My sign is also taken out. Guys, even if I am not looking inside the field, like if I am not visible, you can hear me and see the derivation. So minus Q naught upon 4 pi epsilon naught. This thing is what? Dx upon x square. I can write it as x raised to power minus 2 dx. What would be x raised to power minus 2? Integration x raised to power n dx is what? X raised to power n plus 1 upon n plus 1. This is the formula for integration of x raised to power 1 n. So putting this same formula in here, don't write it here, I am just rubbing it. So you will be left with what? X raised to power minus 2 plus 1 upon minus 2 plus 1. Okay, so we will rewrite. The next step would be Q naught upon 4 pi epsilon naught x raised to power minus 2 plus 1, that is minus 1 upon minus 1 infinity to R. This negative sign and this negative sign you can cancel out. So you are left with Q naught upon 4 pi epsilon naught x raised to power minus 1 is what? 1 upon x infinity to R. How do you put the limits? Upper limit minus lower limit. So you are left with Q naught upon 4 pi epsilon naught 1 upon R minus 1 upon infinity. What is 1 upon infinity? 0. So this term is 0. Hence total work done, this from there, total work done is 1 upon 4 pi epsilon naught q naught upon r. Now from here I'll continue the same point at this point. Total work done is this. So according to formula of potential, work done 1 upon 4 pi epsilon naught q naught upon r whole divided by q naught, which gets cancelled out. So the final equation for the value of potential is 1 upon 4 pi epsilon naught q upon r, right? And do not forget that this is scalar in nature. So whenever you guys will be using this formula in numerical, you will never, or you will always take the sign of the charge. You have to take the sign of the charge because this is a scalar quantity. Let us recapitulate few points. First thing which we did was electric force, electrostatic force, formula was k q1 q2 upon r square. It was vector in nature. So whenever you use that formula in the numerical, you will not take the sign of the charge. Positive and negative charge are there just to do what? Just to represent the direction of force. Similarly, in electric field, the formula was kq upon r square. You would still not take the sign of the charge. The sign of the charge will give you the direction of electric field. If for positive it is outwards, if for negative it is inwards. But in case of electric potential, the formula comes out to be kq upon r, and in this case you will be taking the sign of the charge. Okay.